Hello and welcome to section 5.3 continued. We're going to keep talking about diagonalizability and try to get at a better understanding of how eigenvalues with multiplicity greater than 1 impact diagonalizability. So if we want to diagonalize a matrix, remember that we need to compute our eigenvalues first. And we do that by subtracting lambda from the main diagonal, which gives us a determinant of 1 minus lambda squared. And when we set that equal to 0, we see that we have one eigenvalue that has multiplicity 2. We can actually see that since this is a lower triangular matrix, we could see those two eigenvalues on our main diagonal. So now we need to try to see, so we have multiplicity 2, and in order to determine diagonalizability, we need two linearly independent eigenvectors. And so since we only have one eigenvalue and it has multiplicity 2, it needs to have two vectors in a basis. So let's try to see what happens for this particular. So we're looking for solutions to ax equals lambda x, which is just x here. And so this ends up being a minus the identity times x equals 0. That's what we're trying to solve. So we do a minus those ones, so we have 1 minus 1. So basically we replace our lambda with what lambda actually equals, and we get a new matrix. We can do a row reduction, which is just a simple row swap to get this into reduced echelon form. And now we see that x1 equals 0 and x2 is free. So all of our eigenvectors are going to look like 0 and then x2. So in other words, multiples of 0, 1. And so our basis for the eigenspace of A at eigenvalue 1 is just simply the vector 0, 1. And that's a one-dimensional eigenspace. And we needed 2, so this is not diagonalizable. Okay, so for your quiz, we have another example, and just to make sure we're all clear on how to do this, so to test for diagonalizability, that's a mouthful. And I didn't write it right either. Diagonalizability. So first you find your eigenvalues. Okay? And if A is an n by n matrix, let's go ahead and assume that so we can think about this in general. For this particular case, we're looking at 2 by 2 matrix. If you have n distinct eigenvalues, then your matrix A is diagonalizable. Because remember, each different eigenvalue gives an eigenvector that's linearly independent of the others. But if not, if you have any eigenvalues with multiplicity greater than 1, you need to find the dimension of their corresponding eigenspaces. So you don't have to do anything with the ones that are multiplicity 1, which is kind of nice. That can save you a little bit of time. And if for each of these eigenspaces, if the dimension of that eigenspace equals the multiplicity of the corresponding eigenvalue, so in other words, if the number of vectors in a basis for the eigenspace equals the multiplicity of the eigenvalue for all of these eigenvalues, or for each of these eigenvalues. Let me say it that way. Then your matrix is diagonalizable. And so we found up above something of dimension 2, and sorry, it's an eigenvalue of multiplicity 2, but the dimension of the eigenspace, which remember is the number of vectors in a basis, that dimension wasn't as high as the multiplicity, and so we were not diagonalizable. Okay, so now we can talk about nilpotent matrices. These are just a nice place to generate some examples. And a nilpotent matrix is a matrix that if you raise it to a certain power, it becomes the zero matrix. And here we're going to do the zero. So oftentimes we've used a zero with bars on it to mean the zero vector, but here we're using the zeros to mean the zero matrix. And you might at first think, oh, if I have a real number and I raise it to a power and I get zero, then that number must have been zero to begin with. Well, that's not true for, if you take the matrix 1, minus 1, 1, minus 1, and multiply it by itself, let's look carefully at what happens just to make sure I did this right. So then we get, our first entry is 1 minus 1, our second entry is minus 1 plus 1, and then on our second row we have again a 1 minus 1, and we get a minus 1 plus 1, and you see those are all zeros. So a nilpotent matrix doesn't have to be zero to start with. But here's something kind of neat about nilpotent matrices. Their eigenvalues all have to be zero. And the reason for that is if you take ax equals lambda x, and let's say we multiply both sides of that by a, well, that gets lambda times ax, but we already said that ax was lambda x, so this becomes lambda times lambda x, and so that becomes lambda squared x. And we keep going, we get a to the k times x equals lambda to the k times x. But now a to the k is 0, and so what we have is 0 equals some constant times x. But x is an eigenvector, and so x cannot be 0. So lambda to the k must be 0. And now lambda, unlike the matrices, lambda is a real number. So since lambda is real, then it has to be 0. We can't raise a real number to the k and get 0, even though we can for matrices. And so the only eigenvalue is 0. And this allows us to prove something kind of neat. Namely, if A is diagonalizable, which means we have P dP inverse, and nilpotent, which means our diagonal matrix with our eigenvalues on the diagonals is just 0, so then A equals P times the 0 matrix times P inverse, and when we multiply a matrix by the 0 matrix, we get the 0 matrix. And so, in fact, if A is diagonalizable and nilpotent, then A must be the 0 matrix itself. Okay, so now let's look at another matrix and let's calculate the characteristic polynomial, which remember we get by subtracting lambda I and then taking the determinant. And so in this case, we have, we're just subtracting lambda from that main diagonal, which is where our determinant lies. And so here is our characteristic polynomial, and our eigenvalues are lambda equals 4, which has multiplicity 2, and lambda equals 2, which also has multiplicity 2. And then our first question asks us, well, what values of h make this eigenspace for lambda equals 4 two-dimensional? So what we need to do is we need to first subtract 4 times the identity. And so that gives us a 0 on the first row, minus 2 on the second row. Okay. Got momentarily oh, and then I have to subtract 4 minus lambda and a minus 2 on that last row. And so if we do some row reductions, we can take row 2 and add row 1 to it. And that's going to give us 0, 0, h plus 3, 6. And then we can take our third row and divide by 3, and our fourth row and add 2 times what's now our third row, and we end up with this thing. So we have pivots here for sure, so this column is a free variable. And if we want 2 dimensions, we need this second column, this third column, to also have a free variable. And so we need that h plus 3 to equal 0. So h equals -3 is the only possibility to make that eigenspace 2-dimensional. So for your quiz, you need to do the same type of thing, but this time you take a minus 2 times the identity. So you'll end up getting like a 2, 2, 3, 3, 0, let's see, 0, 0, h, 3, sorry, I'm scrolling back up, 0, 0, 2, 3, and 0, 0, 0, 0. And so what you want to think about is, and again, here we have one of our free variables. How are we going to be able to make another free variable happen? And so you want to think about what values of h are going to work for that. Okay, so now based on our answers above, we need h equals -3 to make the eigenspace of A4 2-dimensional. And hopefully on your quiz, so if you didn't get this right, you can go back and redo it. We should have gotten that h equals 2 to make the eigenspace of A at eigenvalue 2-dimensional. And that's because when you, if h equals 2, we can go back up and look at that now, we get 2, 2, 3, 3, 0, 0, 2, 3, and that third row goes away. If h wasn't 2, then we'd wind up getting, we could make that 2 go away and make a pivot in that third row. But we can't have h be -3 and h be 2. So h can't be both -3 and 2 at the same time. So this matrix is not diagonalizable. If h were -3, right, then this here would be, we'd have -3 and 2, oops, and we'd end up getting 3 pivots. And so we'd have only 1 free variable. And so we'd have eigenspace 1-dimensional for lambda equals 2. And even if it was 2-dimensional for lambda equals 4, then we'd have 3 linearly independent eigenvectors, and what we want is 4.